Okay, let's start off with the basics of matrices and vectors. So starting with matrices, we denote a matrix by a capital letter A, and we say it's a M by N matrix, meaning it has M rows and N columns, and the entries of that matrix are A11, A21, so the first index indicates the row number, the second index indicates the column number, down to, so we've got down to M1 here. In the first row we have A12 across to A1n, and then excuse me, AMN there. There we have our matrix. Okay, so the typical element of that matrix is the ijth element, which we denote Aij, or sometimes we'll put the matrix in brackets and put the indices outside. Okay, so one thing we'll often do with matrices is take the transpose. So the transpose of a matrix is defined by switching the indices around. So the rows become columns and the columns become rows. Right? So if we're going to take A transpose, then the first column of A will be, the first row of A will become the first column of A transpose. Okay, so in other words, A transpose Ij is the ijth element of A transpose is the jith element of A. So let's look at a simple example of a matrix. So if we define B to be the 2 by 3 matrix, so it's got 2 rows, 3 columns. The entries of that are 1, 1, 1, minus 1, 3, 1, and 6, 2, 2. So if we take B transpose, that'll be a what'll that be? A 3 by 2 matrix. So it's going to have 3 rows and 2 columns. The first row, the first column is just going to be the first row of A. So we'll take minus 1, 3, 1, and the second column will just be the second row of B. 6, 2, 2. Okay, so if we've got a couple of matrices, say we've got 2 matrices A and B, and A is a K by M matrix, and B is a M by N matrix, right? So A has the same number of columns as B has rows. Then we can take the product of these two things. We can define a third matrix C, say, equals A times B, where an element of C is just going to look like this, right? So the ijth element of C, we're going to take the ith row of A, and we're essentially going to multiply that by the jth column of B, and we're going to look at the pairwise, the element-wise products of those things, and then we're going to sum them up. So we're going to go alpha equals 1 to n. Okay, so it's probably best if we look at an example of that. Let's just change the letters we're using a bit. So let's define a matrix C to be a a 3 by 2 matrix that looks like this. 2, 3, 1, minus 1, 1, 1. We'll define D to be the 2 by 2 matrix 2, 1, 1, 0. Okay, and so we're going to calculate C times D. All right, so let's just move D over a little bit, and we'll go, oops, we'll write that there. And okay, so we've got, we've got C times D. We'll write that there. C times D, right? There, the number of columns of C, which is 2, right? So that's 3 by 2. That's 2 by 2. So we're going to end up with a 3 by 2 matrix as the product. And the first element is going to be, we're going to take this row of C, we're going to multiply it element-wise by this column of D. So we're going to get 2 times 2 is 4, plus minus 1 times 1 is minus 1. Similarly, we go on, we get 2 minus 0, 6 plus 1, 3 plus 0, 2 plus 1, and 1 plus 0. So our final product is 3, 2, 7, 3, 3, 1. Okay. Okay, so let's now consider a vector, which is just really a special case of a matrix. A vector, which we typically denote by a lowercase letter, is simply a matrix with one column. So the m-dimensional matrix, the m-dimensional vector A has elements A1 up to AM. And notice that by default we write A as a column vector. If we wanted to talk about row vectors, then we look at A transpose, which is still m-dimensional, and it is has elements A1 to AM laid down in a row like a row like that. Okay. What do we want to say about vectors? Well, we can think of them as geometric objects that have a length or a magnitude and a direction, right? So we can visualize this easily in a two-dimensional space. So let's set our dimension m equals 2. And let's take an example. The vector A equals 3, 1, right? So how do we draw that in space? Let's just draw a couple of axes. 1, 2, 3, 1, 2, 3. Then here's the point 3, 1 is there. And so the vector 3, 1, A equals 3, 1 is just right there. And so the thing has direction, and it has this magnitude or length, which we're going to call, we'll use double bars. That's the magnitude of A. Okay, so now we've defined vectors, we can look at a couple of common vector products. So the first is the dot product or the inner product. And so we've got two vectors A and B of the same length, right? So they're m-dimensional, so we can think of them as m by 1 matrices if you like. then the dot product A dot B is defined by A transpose times B, right? So A transpose is going to be 1 by M, B is M by 1, so the resulting product is going to be M by 1. So the resulting product is just going to be 1 by 1, so it's just going to be a scalar. And so that's just the sum of AI times BI, where I is a sum from 1 to M. Right, so if we want to write that out, it's A1 B1 plus A2 B2 plus AM BM. Alright, there is a second definition of this, if we can think of it, if we want to think of it geometrically, and it's the magnitude of A times the magnitude of B times the cosine of the angle between them. Right? And what's the angle between them? Well, if we've got the vector B there and the vector A there, then this angle is theta, and we can look at what the magnitude of A times cos of theta is. Right, so this is a right angle down there, and so this is A cos theta, and so we multiply that length there by that length there to get A dot B, right? So let's look at a very simple example of that. Say A equals 3, 1, and B equals 1 minus 1, then A dot B is just 3 times 1 plus 1 times minus 1, which is 3 minus 1, which is 2. Okay. Interestingly, if we think of excuse me, if we think of the geometric definition of the dot product and think of taking the dot product of A with itself, then that's just the magnitude of A times the magnitude of A times the cos of the angle between A and A, right? The angle between A and A is 0. Sorry, that should be a 0, not a theta, right? And cos of 0 equals 1, right? So we've just got the magnitude of A squared, right? So we can, that means we can think of the magnitude of A, or find what the magnitude of A is, just by looking at the square root of the dot product of A with itself, right? Or if you want to write it out in this way, it looks like that, right? And notice for the magnitude of A, we'll often write that just with single lines, right? Rather than that double bar. Right? The double bar typically means a norm. Right. So let's just go back to our little example. A was, what was it? 3, 3, 1. So the magnitude of A is just 3 squared plus 1 squared square root, which is the square root of 10. Okay. So we can define a second product on vectors, right? So here, if we've got A is an m-dimensional vector and B is a n-dimensional vector, right? Then we can we can take what we call the outer product over A and B. And what is that? And that is the product A, B transpose. Right? A, B transpose. So that's going to be M by 1 times 1 by N. So if we look at those together, that's going to be M by N. And so the outer product produces M by N matrix. Right? So if we've got our example we were looking at before, where A was, say, 3, 1, and B was, say, 1 minus 1, so B transpose is a row vector, then we get the 2 by 2 matrix resulting, which is 3 times 1, which is 3, 3 times minus 1, which is minus 3, 1 times 1, which is 1, 1 times minus 1, which is minus 1. And there's our outer product. Finally, I guess because we're going to be dealing with it a lot in this course, we should look at the product of a matrix with a vector. And we often think of that as applying the matrix A to the vector X. Okay, so so A is a M by N dimensional matrix. X is a n-dimensional vector, right? So that's n by 1. So that's going to produce the vector, which is m-dimensional, right? So it's just got m entries. And the ith entry of y, so where yi is just going to be what is that? The ith row, the ith row of A multiplied by X. Right, so J equals 1 to 1 to sorry, what is that? 1 to M. Sorry, that should be 1 to N, shouldn't it? Okay, so let's look at a quick example. Suppose A equals, 2 minus 1, 3, 1, 1, 1, and X is, I'll just write that. So A times X. X is the two-dimensional vector 2, 1. Or should we say 3, 1. And so A times X is going to be, so that's 3 by 2. That's 2 by 1. So the result is going to be a three-dimensional vector, and it's going to be so 2 times 3 minus 1 times 1, which is what is that? 6 minus 1, 9 plus 1, 3 plus 1, which is 5, 10, 4. I hope that's right. Okay, so one matrix we're going to come up against again and again is the identity matrix. So the identity matrix of dimension n is denoted by in, like that. It's an n by n matrix, meaning it has n rows and n columns, and the form of it is that it looks like, so it's a square matrix, and we've got ones down the diagonal, and we've got zeros everywhere else, right? Okay, so we've got zeros everywhere except for on the diagonal. And it's called the identity matrix, and the basic effect of multiplying by the identity matrix is that it does nothing, right? So if we've got A, which is n by n, and we multiply A by in, then we get A back, and if we multiply on the other side by in, we also get A back. And similarly, you can multiply, if we want to multiply m by n matrix by the identity matrix, then, on this side, we'll multiply it by im, and on the other side, we'll multiply it by in, right? And in either case, you get A back. One question that will come up against again and again also is given a matrix A, assuming it's square, right? So it's an n by n matrix. Is there some other matrix, say A inverse, such that A times A inverse equals the identity matrix, which is equal to, A inverse times A, right? Does there exist some matrix A inverse that has some such property? If such a matrix exists, so if A inverse exists, then we say A is invertible or non-singular. And if no such A inverse exists, if not, A is singular. Right? The problem of actually finding the inverse is a very hard problem, and particularly for a high dimensional A. So let's talk about a quantity known as the determinant of a square matrix A. So we've got A, an n by n matrix. Then we denote by det A, or A surrounded by the absolute value signs, the determinant. And so we're not going to give the to write down the formula for the general determinant. It's kind of complicated. Look it up on Wikipedia maybe. But in a couple of special cases, it's simple enough to write down. So when n equals 2, the determinant of A, right, is just that thing. And so let's say A is just the matrix with entries A, B, C, D. Then the determinant of that thing is just AD minus CB, right? So we've multiplied those things two together and multiplied these two things together and subtracted them. Okay, in the case of n equals 3, then if our matrix A has entries, so let's say it has entries A, B, C, D, E, F, H, I, J. Okay, so what we're going to do is we're going to multiply down here, adding these products, right? So we're going to get AEJ plus BEJ plus CDI, and we're going to, let's use a different color here, so we're going to subtract these products coming up from the bottom, so that one and that one. Okay, so let's go back to black. So we've got HEC minus IFA and minus JDB. Okay, and this quantity, the determinant, well, it sort of tells us about the scale of transforms. So if we're going to be looking at something like, you know, A applied to X, the determinant tells us, you know, how grossly it tells us how much A scales X. Okay, so let's just look at a quick example. Suppose A equals 3, 5, 1 minus 1, then the determinant of A is just 3 times minus 1 minus 1 times 5 equals minus 3 minus 5 equals minus 8. Okay. The determinant has a bunch of interesting properties that can make finding the determinant relatively easy, right? So first is that the determinant of the identity matrix is always 1. Second is that transposing a square matrix has no effect. Sorry, let's just go back. That should be a transpose. Then transposing a square matrix has no effect on the determinant. Right? If A has an inverse, then the determinant of the inverse of A is just 1 over the determinant of A. Okay. If we've got two square matrices, A and B, then the determinant of A times B is just the determinant of A times the determinant of B. Given a scalar C, if we multiply each element of A by C and we take the determinant of the resulting matrix, then that's just going to be the determinant of A multiplied by that scalar raised to the power of n. And remember here, A is a n by n matrix. Okay, so let's start looking at eigenvalues and eigenvectors. Right, so we say an eigenvector. No, so let's start with a square matrix again. It's n by n matrix. Then E is an eigenvector if A times E equals lambda times E. Okay, here E is a non-zero vector, right? So the zero vector is just the vector which is a bunch of zeros. So E is a non-zero vector and lambda is scalar, and it could be 0. Okay, so E is known as the eigenvector, an eigenvector, and lambda is known as an eigenvalue. Okay, so essentially that's saying the effect of applying A to E is just all we get when we multiply A by E is that E gets scaled by some amount given by lambda. Okay, so how do we go about finding these eigenvalues and eigenvectors? Well, we can use a determinant to find the eigenvalues of A. Indeed, after some manipulation of this identity, so if we have A, E equals lambda times E, then we notice that that is just the same as lambda times n times E, right? And so that implies that A E minus lambda I n E equals the zero vector. Okay, and we can pull the E out, right? So lambda I n equals E equals 0. Now, these are matrices and vectors, so we can't just say that either this must be 0 or this must be 0, but if we take, but we can say that if this matrix here has this effect on the non-zero matrix, then the determinant of this thing must be 0. Okay, so we can say that the determinant of A minus lambda I n equals 0. Okay, and that gives us a, it's known as the characteristic polynomial. Right, so let's look at an example. So if we want to find the eigenvalues of this matrix here, 3, 5, 1, minus 1, then we need to solve what we call the characteristic polynomial. P lambda equals the determinant of A minus lambda I equals 0. Right, so what is this determinant? Well, that's 3, 5, 1, minus 1 minus lambda times the two-dimensional identity matrix. Right, so that is the determinant of 3 minus lambda, 5 minus 0, 1 minus 0, and minus 1 minus lambda, which is minus 1 minus lambda, right? And that determinant is 3 minus lambda minus 1 minus lambda minus 1 times 5, right, which is just 5. And so if we do a bit of expanding that out and simplifying, it's easy to check that we end up with this equation here, and factorizing that gives us lambda plus 2 times lambda minus 4. So setting that to 0, we see that lambda is either 4 or lambda is minus 2. So the eigenvalues of the matrix 3, 5, 1, 1a are 4 and minus 2. Okay, so now we found the eigenvalues, let's find the eigenvectors corresponding with, well, let's just look at one of the eigenvalues. So our matrix is 3, 5, 1, minus 1, that's A, and we saw that one of the eigenvalues is lambda equals minus 2. So let's find the eigenvector corresponding to that eigenvalue. So we want to find E, let's call it E1, E2, those are the elements of E, and it satisfies A, E equals minus 2E. Right? So if we write that out fully, A times E gives us a set of linear equations, 3E1 plus 5E2 equals minus 2E1, and what have we got? E1 sorry, minus E2 equals minus 2E2. Right? So let's solve that first equation, or rearrange that first equation. We get 5E1 plus 5E2 equals 0. So that means E1 equals minus E2. The second equation, what do we get? Just move the E2 across to the other side, I guess. So we get E1 equals minus E2, right? And so that's both equations reduced down to the same, produce the same result. So we've got two free parameters in E1 and E2, but we've only got one equation to explain them, right? So that means we can fix one of the parameters, say E1 equals 1, and that implies that E2 equals minus 1, right? So E equals 1 minus 1 is an eigenvector. And it turns out that anything of the form E equals C minus 1, 1 is an eigenvector corresponding to the eigenvalue lambda equals minus 2. Okay, and typically choose C such that the size of E is 1, right? So that means it's normalized. So here we'll choose C equals 1 over root 2. So we say two vectors A and B are orthogonal when the dot product A dot B is 0. So when does that happen? Well, remember that A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. Right, so assuming A and B are non-zero, right, so they have greater than 0 magnitude, then that means to make this thing 0, this cosine of the angle between them must be 0. And when is that 0? Well, that equals 0 when theta equals pi over 2, right? So in that case, so if we've got our vector A and our vector B, then the angle between them is a right angle, right? So, in two-dimensional space we'll say, three-dimensional space we'll say things are perpendicular, and generally we'll just say A and B are orthogonal to each other. So that extends the idea of perpendicularity. When we're talking about sets of vectors, say we've got a set E1 up to En, well, we say that set is mutually orthogonal exactly when any pair of distinct vectors we take from that set is orthogonal. So if EI dot EJ equals 0 for EI not equal to EJ. Right? We say a vector EI is normalized So EI is normalized when it has length 1. Right, so that means, right, so if we take the dot product of EI with itself, then that's going to be 1. Right, or, the square root of that. And so, coming back to the set, if the set is mutually orthogonal and each vector within it is normalized, then we say that that set is orthonormal. So set is orthonormal when so it's mutually orthogonal and each member is normalized. So there's a nice result around vectors A that are square and symmetric. So square is the thing is n by n. Symmetric means that the transpose of the matrix looks the same as the matrix itself, right? And in that case, so if A is square and symmetric, then A has n eigenvectors which are mutually orthogonal. Mutually orthogonal. Right, so the eigenvectors of A form a mutually orthogonal set of size n. And if we're given any square matrix A of size n with n mutually orthogonal eigenvectors, then we can represent the matrix in this sort of decomposed form where A equals the sum of I equals 1 to n of lambda I EI transpose, right? And we call that thing UI. Right? So here lambda I is the ith eigenvalue, and EI is the ith eigenvector, right? And so this UI is a n by n matrix formed by taking the outer product of EI, and so we've seen this is like an eigenvector expansion of the matrix A. Okay, let's finish with a few quick definitions. So we'll let A be a m by n matrix. Then we define the range of A, so range A, to be the set of m-dimensional vectors such that there's some other vector x that when we apply A to x, we end up with y. For some x, okay? And that's also referred to as the column space or the span of A. Column space or the span, okay? And then the rank of A is just the dimension of the range. So that's the number of mutually orthogonal vectors that we need to describe the range. Dimension of range of A. And finally, let's define the null space of A, or which will denote null A. So the null space is just that set of vectors x that when we apply A to them, we end up with the zero vector.